Welcome to the next video in the Combinatorics series, discussing Chapter 1, Enumerative Combinatorics. In this video we will solve problem 1115 from the textbook. And this one's a doozy. We will investigate the prime divisors of 2n choose n. It is probably best to introduce this by way of an example. So consider the case when n equals 5. The prime factorization of 10 choose 5 is 2 to the 2, 3 to the 2, times 7. Let's start by investigating 2, which has exponent equal to 2, in the prime factorization. Let's now compute 10 over 2 to the k, rounded down, for several choices of k. First 10 over 2, rounded down, is 5. This is odd, so let's add this to a tally. Next 10 over 4, rounded down, is 2. This is even, so let's skip this one. Next 10 over 8, rounded down, is 1. This is odd, so let's add this to the tally. After that, every 10 over a power of 2 will be 0, so we are done with our tally. Notice that we counted a total of 2 values of k such that 10 over 2 to the k, rounded down, is odd. But if we find the power of 2 in the prime factorization of 10 choose 2, then that power is also 2. What we will prove is that this always happens. That is to say, if p is any prime, which divides 2n choose n, let alpha be the power of p in the prime factorization. Then alpha is the same as the number of k such that 2n over p to the k, rounded down, is odd. To get initial traction on the problem, it seems like a good idea to express 2n choose n as 2n factorial over n factorial squared. We can try to get a somewhat naive count of how many factors of p are in the numerator and denominator. Just because it seems simpler, let's start by counting the factors of p in n factorial. As we march along 1 times 2 times 3 times 4 and so on, up to n, we will find a first factor of p. After that, if it shows up, we may find 2p, which gives another factor. And then we find 3p, and so on. Eventually this runs out, so the question is, when? Let's say that the final factor which we find is mp, so that mp is less than or equal to n, but m plus 1p is not. Then m is the largest integer, less than or equal to n over p. This is equivalent to the fact that m is n over p, rounded down. However, this does not count all of the factors of p, because, at some point in the counting process, we may have encountered p times p. But for this factor, we counted only one factor of p. Likewise, we counted 2p squared only once, and so on. Like before, now the question is, how many times is p squared a factor? And as before, it will be n over p squared, rounded down. Of course, this process continues also, so that we again get extra factors of p by counting p cubed, and the number of them is n over p cubed, rounded down. Continuing likewise, we now have an answer for how many factors of p are in n factorial. The answer is n over p to the k, rounded down, summed for k from 1 to infinity. The exact same logic as above tells us that the number of factors of p in 2n factorial is 2n over p to the k, rounded down, summed for k from 1 to infinity. We are therefore ready to say how many factors of p are in 2n choose n. Of course, we take the factors from the numerator minus those in the denominator. This gives us 2n over p to the k rounded down, then minus 2 times n over p to the k rounded down, all summed for k from 1 to infinity. At this point, let's think hard about this 2n over p to the k rounded down, then minus 2 times n over p to the k rounded down. To keep things as simple as possible, let's think instead about 2a, rounded down, minus 2 times a, rounded down. If 2a, rounded down is even, suppose that it is 2x. Then 2a is a number between 2x and 2x plus 1. Then a is between x and x plus half. Then a, rounded down, is x. Whence 2a rounded down, minus 2 times a rounded down, is 2x minus 2x, which is 0. One can then also go through a very similar process to see that when 2a rounded down is odd, then 2a rounded down minus 2 times a rounded down is 1. This effectively shows that 2a rounded down minus 2 times a rounded down is 0 or 1, depending on the parity of 2a rounded down. Of course, the intention is to use a equals 2n over p to the k. The above therefore shows that the sum is a sum of ones, precisely as many as there are k such that 2n over p to the k rounded down is odd. Therefore, it counts the k such that 2n over p to the k rounded down is odd.
We can then use this to quickly find the prime divisors of 18 choose 9. For instance, to decide if 2 is a prime divisor, we need only investigate values of floor 18 over 2 to the k. In fact, for k equals 1, this is 9. Since 9 is odd, the power of 2 in the prime factorization is at least 1. Hence it is a prime divisor. Likewise, we find that floor 18 over 3 is 6. so we skip this. Floor 18 over 3 squared is 2, so we skip again. And every floor 18 over 3 to the k after this is 0, so 3 is not a prime divisor of 18, choose 9. Floor 18 over 5 is 3, so 5 is a prime divisor. Floor 18 over 7 is 2, so we skip. Floor 18 over 7 to the k for every other k will be 0, so 7 is not a prime divisor. Floor 18 over 11 is 1, so 11 is a prime divisor. Floor 18 over 13 is 1, so 13 is a prime divisor. Floor 18 over 17 is 1, so 17 is a prime divisor. And there are no other prime divisors. We can confirm this result by seeing that the prime factorization of 18, choose 9, is 2 squared times 5 times 11 times 13 times 17